Hello friends and engineers, are you ready to write your Arduino code like a professional embedded programmer? If you are tired of using fancy libraries and built-in functions like pin mode and data write that slow down your Arduino code, and you're ready to write low-level register code that is fast and efficient for raw microcontroller control, this is the right video for you, as I'm going to be walking you through register level programming that can enable you write clean code that is directed towards the hardware, direct hardware programming. So guys, in this video, I'm going to show you how to master register level programming, starting with how the Atmega 328P microcontroller works, how to understand datasheet, and then we'll end with two real-world mini projects using only register level code. So the two projects that was initially showed in the intro section of the video, the traffic lights project and the button controlled LED project, we're going to be using that to understand register level programming. So to understand register level programming, you have to understand the microcontroller you're working with. In this case, the Atmega 328P microcontroller, which is an 8-bit microcontroller, as you can see on screen, and it comes with a 32 KB flash memory. That is where your program code is stored. It's non-volatile, meaning it doesn't get erased when the power goes off. The microcontroller also comes with a 1 KB EEPROM, electrically erasable programmable read-only memory that is used to store data permanently even when the power goes off. So the controller also comes with a 2 KB SRAM for variables and runtime data. So this is like working memory, just like you have your notepad that is used while your program is running. So it stores variables, function call stacks, and buffers. But once the power is lost, all SRAM data is wiped. Alright, so on screen you can also see that the Atmega 328P comes with 23 I/O pins. So it comes with 23 input and output programmable pins, and it also comes with 6 analog input channels. That's for your ADC, analog to data converter. So there are other features of the Atmega 328P, such as UART, SPI, I2C, timers, PWM, pulse width modulation, and then ADC that we just mentioned earlier, analog to digital converter. So for the ADC of that's the analog to data converter of the Atmega 328P, it has a 10-bit resolution that's between 0 to 1023. It also converts analog voltages that's 0 to 5 volts into data values. So like we already said, it has 6 analog input channels. That's for Arduino Uno, that's A0 to A5, that is normally used for sensors and knobs. So the controller also comes with UART that handles communication over USB for debugging, communicating with modules like Bluetooth and GPS. So for the SPI, which is the serial peripheral interface, it's fast for communication with devices like SD cards, displays, and shift registers. So guys, still talking on the features of the Atmega 328P microcontroller, let's look at the datasheet to get more insight. So go to your browser and head over to Atmega 328P datasheet. So you can use any browser, I'm just using Chrome. So head over to microchip technology, and here we go. This is the datasheet. You can see the various features we've already talked about earlier. Talked about the 32 KB flash memory, we talked about the 1 KB EEPROM, the 2 KB SRAM, and a whole lot of other features that are here that we didn't even mention. It also even have special microcontroller features like the external and internal interrupt sources. So these are the I/O packages, the input and output parts, which is what we're going to be focusing on largely in this video because of the project we're working on. Our focus is on general input and output configuration using register level programming. So this is the operating voltage, 2.7 volts to 5.5 volts for the Atmega 328P, and this is the temperature range. Alright, so since we're going to be focusing on the pin configuration of the ATmega 328P. Let's head over to the page that has the input and output part. So I already know this because I have used this data sheet before now. So I'll just head over to it without wasting much time. So this is the input and output part, and this is how to configure the pin. So you can see this Roman figure 3.21, that's configuring a pin. It says each port pin consists of 3 register bits: DD-XN, port XN, and pin XN. Now this DD means data direction. That's how the manufacturers called it. That's for the register now, data direction. So this data direction, this is where you get to set your ATmega 328P. You get to set the pin as either an input, or you set it as an output. Alright, so the X here, it just talks about which of the particular register you are talking about. That's which of them do you want to set as input or output, because they come in either A, B, C, or D. Alright, so we're going to be seeing this in more details. I would head over to the maybe a summary of the register so that you understand this in detail. Then the port is just like your data write. This is where you get to write to the output pin that you have declared in the DD-XN. So this port is to talk to your port to either make it high or low. That's for your output. So the port is mainly for the output, to write to the output to make it high or low. So this X is still dependent on which of the ports. Is it port A, or is it port B, or port C, or port D? So the N is which bit. All right, so it can be, because since this is an 8-bit microcontroller, so it's between 0 to 7. All right, so which of the bits is the ports that we're looking at? Is it port B2 that you want to tell to be low or to be high, or it is port B7? So that's what this port XN is all about. And the pin is more like an input address. It's an input address. All right, so this is the pin where we get to collect data from the external world, maybe like from sensors or from buttons. So this is more like when you want to work with input devices, you use the pin. So this pin XN, the X, still which of the exact pin do you want to configure? Do you want to configure pin A or B or C or D? And then the N is which exact bit in that pin A or pin B do you want to configure? So that's just everything you need to know. So the manufacturers have stated clearly that each port pin consists of 3 registers. So DD, XN. So the DD is data direction, to either set your pin as as input or output. All right, so you either set your pin as input or output. Now when you're done setting your pin as input or output, if you set it as output, so this port is to write to that DD, which is data direction, to write to it to either be high or to be low. Then the pin is for input address. All right, so that's it basically. And I think to get more of the register description, let's head over to page 72 to give us more insight so that we can really understand and master how to configure the GPIO of ATmega 328P. So this is page 72. can check out the register description of the microcontroller. Exactly, this was what I was talking about. So you can see port B, you can see port B data register. You can see these are the various bits. So DDROB, data direction register, that's for port B, and there is also port C. So this is how the manufacturers, they named the ports, that's the GPIO, the general input and output pin. So if you want to work with input and output, you already know exactly how to write to it, but I'll go into more details by discussing on the pin structure and the pin layout. But with this, you already have an idea of how to interact directly with the register of the Atmega 328P, like with this information and how it's configured, how to declare your, or how to set, you can also say declare, how to set your input and output, and how to now write to your output, and then how to also write or read from your input. So by following the manufacturer's guide, which is the datasheet. So with this information from this datasheet, it will enable us to write directly to the register of the microcontroller, the Atmega 328P. So once you understand this very well, it will also help you. You read the datasheet for other microcontrollers like the STM32 and even the Texas MPE microcontroller. So that's pretty much all the details we need for the input and output configuration in this video. So we're not going to be looking at PWM, the information on PWM and timer. Why? Because this video is strictly for the general input and output pin, and the project we're going to be working on is also limited to the configuration of input and output pin, which is the traffic light projects. We're going to be focusing on configuring it as an output because it's largely output, and then the button controlled LED, it's input. So we're going to be stopping at input and output here in the datasheet. So we're not going to fill our heads with too many information. All right, so let's head over to the pin structure, the layout of the Atmega 328P. So guys, let's talk about the pin layout and the port structure of the Atmega 328P. So from the datasheet, we'll find out that the microcontroller has three main I/O ports: port B, port C, port D. So each of these ports controls a group of 8 pins, and you can use them to read input or write output. Right? So those are the three major ports, just as we saw on datasheet and now on screen. All right, so here is how the ports, the three major ports, maps to the Arduino Uno. So port B maps to data pins 8 to 13. Port C maps analog pins A0 to A5, while port D maps to data pins 0 to 7. So when you write something like port B, you are not just controlling just one pin, you're working with a full set of 8 bits. Now each of these ports has 3 important registers: the DDRX, as discussed in the datasheet, and which is the data direction register, where you get to set input using 0 and then output using 1. Then you have port X, that's the output register, as discussed earlier, where you get to write high or low. High 1, low is 0, just as you can see on screen. That's 2 output pins. And then the pin X, that's the input register, where you get to read the current state of the input pins. All right, so we're going to look at an example now, but these are the basic pin. So we already know that to configure a pin as an output, we use port, and we use pin to configure a pin as an input. All right, so for our traffic light project, we're going to be using the port. So port X, the X is changing, so it can be either port A, port B, or port C, or port D. And we use 1 and 0 to either make that particular port that is an output to be high or 0 to be low. All right, so let's see a case study where we want to make one of the ports to be high. So let's say we're working with PB0 as our output and we want to make it high. So we use the OR operator, and we said once any of the inputs of the OR operator is 1, the output must be 1, 1, which is high. All right. And the opposite of it is when we want to turn off that same PB0, we use the AND operator, and with that negation there is 0, and once there's 0 in input, it is 0. All right, so let's go to the next case study, which is, say we want to turn on multiple bits, which is PB0, PB1, PB2, and PB3. If we want to turn on multiple bits, we can just simply make life easy for us by using this binary. We'll write it in binary. So these are the 8 bits, 0 0 0 0 0. We go to that exact bit. So look at bit PB4 and we'll make it high. Look at bit PB5. So you can write your code this easy and simple and fast. So guys, in order to control the GPIO pins using registers, let's head over to our WorkWe simulator. WorkWe Arduino simulator. This is what we're going to be using so that we can simulate the hardware while writing the code at the same time. So you click on this first query, and then we're working with Arduino. So Arduino Uno. We're using the Atmega 328P. Alright, so let's take a real world example so that we can understand what's going under the hood when trying to use built-in functions in writing GPIO controls. So let's try to turn on this onboard LED that is in this Arduino Uno development board. This is the onboard LED and it's directly connected to data pin 13. Alright, so normally as newbies we turn on the data pin 13. We first declare it as an output, and then we use the built-in function data write to tell that output to be high. And once that is done, simulate is working. Now if you want to write register level code to do the same thing, what is actually happening under the hood, or what's going on behind the scenes of this pin mode pin 13 as output being declared, is that we're going to be writing directly to that register, the ones we've seen from our data sheet. So this is what is going under the hood. So the pin mode pin 13 declared as output. The actual register here is DD, which is data direction register, port B. Alright, we said there are 3 major ports of the Atmega 328P, which is ports B, port C, port D. So now this is one left bitwise DD B5. So if I remove this 5 here, this is data direction B, so it's on all port B. I'm referring to all port B as an output. Remember we said 1 is output, that's to set the the DDP. 1 is output and then 0 is input. So since it's LED we're trying to turn on, we're working with output, so that's why this 1 is here. Now this left bitwise operator is just to shift to a particular bit to be precise. All right, so we're precise to bit 5 in B port, in port B, which corresponds directly to the data pin 13 of the Arduino Uno development board. All right, now under the hood of the digital write, what's actually going down here is this. Port B5. So this is how to write to it. So if you put 0, it means it's low. Remember, it's still bit 5 in port B. So this is what is actually going on under the hood. Now there are two major logic operations that you need to understand, or operators that you need to understand when working with the GPIO pins in register level programming. So one is the AND operator and the other one is the OR operator, which you can see here. So if you remember very well, the OR operator, it works in such that when any of the inputs is 1, the output must be 1. All right, so that's why this is normally used to either set your DDB as an output, or you are using it to write to the port to be high. But if it's AND operator, all right, AND operation work, or AND logic gates, it works in such that if any of the inputs is 0, the output must be 0. So that's why we normally use the AND operation to, denote 0 when writing register level programming, and we're going to be seeing that in a bit. All right, so this is how to turn on an LED using register programming. So let me go ahead and comment this. Let me comment this and run on only the low level register code and see. So LED is still on, so it's working perfectly well. All right, so it's very simple. So if I want to turn off this port, all I just have to do is to do an AND operation. So let me put a delay here. Let me put a delay so that I will just do a blink code. So this is 1 second, and then all I just have to do is to do an AND operation. That's because I'm trying to turn it off. All right, so and then I will negate this. Remember, say the AND operation, if any of the input value is 0, then the output must be 0. All right, so once I put this negation sign here and simulate, we ought to get a blink code here. Okay, sorry, I have to, let me delete this. It should be off for so let me simulate again. Perfect. So this is how to write a blink code using register level programming knowledge. So just understanding this alone, you should be able to built this simple traffic light project that I displayed in the info section of this video. So I'm going to drop the algorithm that will guide you on how to write the code for the traffic light project and even for the push controlled LED. So the button controlled LED project. So because when you're talking about button, you're using input. All right. So we're going to be using pin instead of port. Port is for output. That's why for the traffic light system, we're going to be using port mainly. But for the button controlled LED, we're going to be dealing with input because button is an input device. All right. So, but just understanding what goes under the hood and knowing how to write directly to the register, it's a very good programming practice and it brings more experience. It shows that you are an experienced embedded programmer. Right. So with this alone, you can pause this video here and try implementing the traffic light project yourself and also the button controlled LED yourself and see if you can get it. And I'll see you in the next section, which is to show you the algorithm for the traffic light and the button controlled LED so that we can wrap up this lecture on the GPIO control using register level programming. Moving into the traffic light system, here is the algorithm to achieve the project. If you have been following the lecture so far, and if you followed how I blink the LED, then this traffic light project should be very easy for you to achieve. So the first thing first is to turn on the red LED, which is the stop sign for the traffic light, and you wait for some time, and then you turn on the yellow, you wait for some time, and then you turn on the green. Usually the red is the one that takes a longer time, right, where the vehicles get to stop. So, and that is how the traffic light project work. This is a walkway simulation of the traffic light project. All right, so you should be able to achieve this if you've been following the lecture so far, and if you understood how we blinked the LED using register level programming, then this traffic light project should be very easy for you to achieve without looking at this code right here. All right, so this is a schematic capture of the traffic light project. These are the three LEDs connected to the various pins. The red LED is connected to data pin 2, which in the code is mapped to PD2. All right, we've already looked at the pin configuration or the pin layout of the Atmega 328P. All right, this is the yellow LED connected to data pin 3, which is mapped to PD3. And this is the green LED connected to data pin 8, which is mapped to PB0. Now these are the three LEDs for the these are the three resistors for the three LEDs, and these are limiting resistors to limit the flow of current that is going into the LEDs. This is just to protect the LED from getting bad or damaged. All right, so this is a schematic capture, and now this is the code. So like I said, this works like the LED blink code we've written. So first I just get to define the pin. You can work directly with the pins without defining them like we did in the LED blink code, but this is just a good programming practice so that we can work with the name we can easily relate to and remember, and we can easily use in the program without getting confused or anything. So that's why you can actually work with just PD. Instead of red LED, you can decide to write PD2 that we've been doing, but it's just a good programming practice. All right, so I just defined those pins as this, just like a variable. All right, so not variable really, because you're not really storing anything, you're just defining a name, all right, to be what you want it to be. So the first thing is to configure your output pin. You know, previously we used pin mode, but since this is register level programming, we use the data direction register configuration, and we already talked about how to achieve that. So this is the 3 digital outputs we're going to be working with. The 3 output devices, the red, yellow, and then the green. So this is how to declare them as output. And after declaring them as output, the next thing is to now write to each of them. So the code is very easy in the sense that the only thing you're just doing is to give priority at a particular time to one of the LEDs, and the next time you give priority to the other LED, and until you get to the final one. So but it's just that the only thing we're manipulating here is really the time, the delay. All right, for the green LED we're using 3000 milliseconds, which is 3 seconds. All right, then for the yellow and the red we're using 1000. So depending on how you want your traffic light project to work, you can change the delay. All right, but the most important thing is to understand the concept. First, we already know how to declare our output pins. We already know how to configure our output pins working with the data direction register, and we already know how to write to that exact bit we're working with. All right, so we know that we're not working with the entire port D. All right, we know that we're working with a specific one, working with port D2, port D3. All right, and that's why we're using this left bit shift register. This left bitwise sign here is to give a precise control to work with the exact bit that we are trying to control. So once you understand the LED code, then this is a very simple project for you to understand. So let's head over to our next project, which is the button controlled LED. So guys, make sure you drop your questions if you still have any question regarding the video or regarding this project. If you have any question, please drop it in the comment section, and please subscribe to my channel if you're not subscribed, and like this video if you enjoyed this video. You can also suggest any possible projects you would want us to work on, or you want me to work on and put on this channel. All right, so let's move over to our next project. So guys, still on the GPIO control using register level programming, we are now going to be working on a second project, which is the button controlled LED, as a way to learn how to interface input devices with the Atmega 328P microcontroller. So we're going to see how we can use register level programming to interface a push button with the Arduino Uno. So the same way we work with port when we configure a pin as an output is the same way we work with pin when we configure a pin as an input when working with input devices like the push button we're about working with now. So this is pin X. The X here is changing. It means it can be pin B or pin C or pin D that we're trying to configure any of the bits as input. All right, so you can see it's 8 bits from 0 to bit 7. So we get to configure any of the bits in the pin that we're using for this. So guys, in order to read the status of the input pin, we can use the if statement to achieve that. So let's say, for instance, we want to read the status of PB0. So we can say if pin B and left shift PB0, if the condition is true, executes the instruction in that if statement. But if false, then executes the instruction in the else statement. So this is a condition for that we can use to read the status of an input pin. All right, so using a conditional statement, if statement like this, is a right pattern to follow when you want to read the input pin, so the status of an input pin. All right, now let's go further with the example. So let's say we want to read the status of PB0. So first we have pin B. So assume that we have pin B, that is the entire 8 bits is 00000. All right. So now let's look at the one shift pin B0, which means that in B0, which is bits B0, it should be high. So that's why there is 1 there. Now the microcontroller depends on the input device to produce either a 1 or a 0. So the microcontroller is not in charge. So it depends on that input pin. So whenever the button is pressed, which is in pin B, that is when the output, which is the condition now of PB ampersand 1 left shift pin B0 will be true. If the button is not pressed, the pin B will remain 0, and in and 0 1 it will be 0 output. But now when the pin is pressed, so PB0 becomes 1 in pin B. So and once it becomes 1, and looking at the 1 left shift pin B0 that you've set already, it tallies with it, and 1 1, which is having high input, the output will always be high, and that's why the instruction we execute only when the pin B becomes high. All right. So when the button is not pressed, which means all the bits in pin B will remain low, and once they remain low, if you perform the AND operation alongside the 1 left shift bit pin B0, the output will be low. But once the button is pressed, it becomes high in pin B, and then the output. So after understanding the underlying concept in working with input devices, so let's head over to our project, which is the button controlled LED. And here is the algorithm for the button controlled LED. So first is to set your input and output pins, and after setting the input pin that we're going to be working with, which is the PB3, so the next thing is to make sure the internal pull up is disabled. So we're going to be using external pull down to pull down the pin, and I'm going to be showing you how to work with pull up and pull down resistors. And the next thing is to check if the button is pressed or not, and that will determine if the LED should be on or off. And the last step is the basic debounce, and the basic debounce is just using time delay to avoid false triggers that might come from pressing a button, in order for you to have a code that works perfectly well without any error. To explain the concept of the pull up and pull down resistors, I'm going to be using the Proteus 8 software to do that explanation. And this is a pull down resistor. Alright, so how it works: first, if we see from our diagram, the power is connected to one terminal of the button, that is the push button. Then the second terminal of the push button is connected to one terminal of the resistor, and then to a logic probe, which we are going to be using to represent our GPIO pin. That's the signal that is going to our microcontroller. So this is the logic probe, which is the signal that is going to our microcontroller. So this is the 10K resistor, all right, and the last terminal is connected to the ground. So now the concept of push button, how it works, all right, and I'm going to be simulating it in a minute. So when you press the button, current flows and it goes to the logic probe, all right. But when the button is not pressed, all right, this 10K resistor is dragging everything to the ground, all right, and the output to the logic probe is 0. But when the button is pressed, the current flows from that power to the logic probe, so your GPIO pin becomes high. So now I've turned on the simulation and see what is happening. When the button is not pressed, the logic probe is seeing 0. Why? Because this pull down resistor is dragging everything here down to 0. So the resistance here is higher than what you have in the power. All right, that's from the 10k ohms. So everything is dragged down to 0. So it's neutralizing every current down to 0. So the logic probe is seeing 0. But when you press the push button, the current flows from the power straight to the logic probe, so your GPIO pin, which is the Atmega 328P microcontroller that is now receiving it as an input. So in this case, you're getting a high, and what that means is there is no resistance opposing the current, and that's why it's saying a high. Right? So this is how the concept of the pull down resistor works. So there's a resistor that is pulling the currents to the ground to give you 0. All right, so whenever the button is pressed, you get a logic 1, but when it's not pressed, you get 0. This is a pull up resistor, and the pull up resistor is a direct opposite of the pull down resistor we just discussed. So one terminal of the button is connected to the ground, and the other terminal is connected to the terminal node that is connected to the logic probe, and also connected to the terminal through a 10k ohms resistor to the power. All right, so this is the connection of the pull up resistor. So when we simulate, what happens is when the button is not pressed, the logic probe, which is a GPIO to the Atmega 328P, is seen high. Why? Because it's directly connected to the power, so it's seen high. All right, no resistance. All right, so it's just seen high. So current flows through this part from the power directly to the logic probe. But when we turn on the button, the current flows through this part down to the ground. So it follows the path from the power and down to the ground. All right, so it flows through this part and it goes down to 0. So that's why the logic probe, which is our GPIO pin, now becomes 0. But when you turn it off, so once the button is off, the power flows to the GPIO, but when it's on, it flows down to the ground. So this is just a direct opposite. So to remember this, once the button is pressed, the output is 0. Once the button is not pressed, the output is logic 1. Now that we've understood how to configure input pins and how to read the status of input pin, let's go back to the algorithm for the button controlled LED project. So this is just the syntax that matches the algorithm that we're going to be using to achieve the project. So first is to set our output pin, and I'm using PB3. You can decide to set yours to a different pin, and that PB3 matches to pin 11 of the Atmega 328P pin layout. So next is to set our input pin. I'm using PD2. You can decide to change yours. I'm going to be dropping the pin layout so that you get to see the pin layout for the Atmega 328P. So then to enable the pull up on the PD2, which is the input pin, so we'll also save that. This gets to check if the button is pressed. So if the button is pressed, that's PD2 is low, so it gets to save that. Then we come over to the loop. So once you already understand the pull up and pull down resistor method I taught, then you can understand this enable internal pull up on PD2. So the next thing is just the conditional statement that we've already talked about when working with input pins, and then if the condition is true, to turn on the LED, and if the condition is false, to turn off the LED. So that's pretty much it. And the last line of the code is the debounce. So the debounce is the delay, and the goal of the delay is to prevent the error or prevent our code from misbehaving, especially when there is false triggers that comes with pressing a button, because pressing a button can lead to false triggers. It's just to eliminate that error. So this is the Atmega 328P, and this is the pin layout. So we used data pin 2 and data pin 11. All right, so our data pin 2, if you look at it, you can see exactly where it's mapping to, and our data pin 11, so the PB3 PB2 that we're working with, and you can see that it's matching to it. So you can look at this configuration and decide to set any of the pin of your choice that you want to work with. This is the walkway Arduino simulation of the button controlled LED project. So this is our schematic capture, and this is the push button, our input device, and this is the LED, our output device, to indicate when a button is pressed, right? So the push button is connected to data pin 2, which can be mapped to PD2 at the register level. You can decide to use any pin of your choice. So once you can follow the data sheet and follow the pin layout, in fact follow the pin layout, and you can easily work with any of the pin you want to work with, you prefer. All right, so this is the LED, which is our output, and we use a limiting resistor, a 220 ohms resistor, to limit the flow of current, just to protect this LED from getting burnt. All right, so the code is very simple if you've been following the various sections of this video, and if you understood how we configured our GPIO pins. I've done a detailed explanation of that already, so I won't have to go over that. So, and following the algorithm is just to set our output pin, which is the LED, and then our input pin, which is the push button, and then the pull up and pull down mode. I already explained the concept of pull up and pull down resistor. So pull up and pull down resistor, and we see that the major difference between them is what happens when the button is pressed. For pull down resistor, at its default state, the button, when not pressed, the output is logic 0, which is off. So the output is off, 0, but when the button is pressed, the output becomes logic 1. All right, then for pull down resistor, pull up resistor, and its default state, when the button is not pressed, the output is logic 1, but when the button is pressed, the output is logic what, 0. So this is the if statement when working with input, and we've already talked about how if statement helps when reading the status of an input from an input device. All right, so this is the if statement, so that reads when the button is pressed. All right, so it reads if the button is low, if it's, because we're working with the pull up option or pull up mode, so it will check if that pin is low, because in its default state it is high, and that's what we said about pull up resistors. So it will check if the pin is low. So once it reaches low, that's when that particular port, we already talked about ports, that we use this in writing to our output to either be high or to be low. All right, so when you check that pin, since that pin is in pull up mode, I've already explained pull up resistor, and we said in the pull up resistor, when we are using the Pro Tools software to do the demonstration, we said when the button is pressed, it is low, but in its default state it is high, it is giving logic 1. All right, so this code will check if the button is pressed, which means is the button now reading low. If it's doing that, it will execute this instruction here, but if this condition is not met, it will execute the else statement. So here now, the pin, which is this PD2, is high currently, high. All right, so because it is high, it's not reading low. Why? Because it has not been pressed, is in a pull up mode, the LED is off. All right, which is the else. but when the LED is pressed, this will be in the button will be reading low. When the button is pressed, it will be reading low, and this condition gets executed. This instruction here gets executed. So that's how the button controlled LED works. So if you don't understand this code or anything you still need me to explain, please drop your question in the comment section below. And if you like this video, please give me a like, click on that like button. And if you are not subscribed to my channel, if you are new to this channel, please hit on that subscribe button so this video can be recommended for others, for other embedded system developers or Arduino programmers. All right. And also, if you have any project suggestions, any project you want me to work on, and if you have any modification also or any suggestion ideas, just drop it in the comment section below, and I will do well to respond to your comments. And thank you for watching. Thank you for staying back. See you in my next video, and bye bye.